All right, welcome back. So now we've been introduced to the idea of what the derivative is. So let me go ahead and rewrite it again so we don't forget. We learned that the derivative, which is changing y over changing x, is equal to the limit as delta x approaches to 0 of f of x plus delta x minus f of x over delta x. If you haven't watched the explanation as to why and you are interested in knowing how and where this comes from, you can watch my previous video, which is the introduction of what a derivative is and gives you a thorough explanation of this formula. For now, this video is more about trying at least a couple of examples to show you how this formula works. Okay? So remember, derivative is simply just a fancy word for slope. So let's do an example. Let's say that you are given a function. Let's keep it something not too difficult. Let's try like a square root of x plus 1. Okay? And you are asked to find the slope of this graph. Okay? Now, let's think about that for a moment. Well, the square root of x plus 1, just to have a visual, is the square root function that got moved to the left by 1 unit. So we're looking at a graph that looks something like this, right? Now, why am I giving you this visual? Well, let's try to make sense out of this. You're being asked to find a slope of that. Just by observation, you should be able to tell me like, well, wait a second, dude, like that's not even a line. So there's no way that's gonna have like a slope. Its slope should be completely different depending on where you are. So then what that means is, what I would say to that is like, well, you know what, you're right. So you should not be expecting that when you apply this formula that you're gonna get a constant, because if you get a constant, that means that you would have the same slope always, which would be linear, and this definitely shows you that it's not linear. Your slope should be different pretty much everywhere. So then what should we be expecting? Well, we should be expecting a variable slope, which means my answer should have variables in it, okay? So let's tackle it so that you can see what I mean by that. All right, so I want to find the derivative of this. I'm going to use another notation. I know I have this, but I can remember I said f prime is the same thing as dy dx. So I'm going to go ahead and say f prime, which is equal to dy dx. In this case, will be the limit as delta x approaches 0. Okay, now what does this mean? Let's look at this specific part first. It says f of x plus delta x. All right, so that we don't get lost, what that means is that whatever is like, if I had ever given you like f of 2, what that would mean is that you would take a 2 and you would put it in here and then you would solve, right? So like that would be like x square root of 2 plus 1, which is square root of 3, right? Now some students get confused with this, you know, when they don't see a number, but it's practically the same thing. You're being asked to input all of this for this x. So that's what I'm going to do. So that's going to become the square root of, for x, I need to input x plus delta x. There we go. So I got that part done. It says minus f of x. Well, I know f of x is this, so I just got to do minus square root of x plus 1. All over divided by delta x. Okay, so now I just got to solve this limit. Now, this might look a little bit different than the limits that you were used to solving in your limits chapter. Because now you're dealing with, you typically, first of all, did not have a delta x here. You either had like an x approaches something, a t approaches something, but it was just one variable. And then in here, there was always just one variable, okay? As you can see here, this is delta x. So I do have a delta x here, but I have x's, okay? So here's what that means when you're taking a limit. This will dictate what your variable is, which means anything that's not delta x, you need to treat it as if it was a constant, okay? So, according to my techniques for solving limits, the first thing I should try should just be substitution. So if I put in 0 for delta x, that gives me x plus 0 plus 1, which would give me x plus 1 underneath the square root. If I take the square root of x plus 1 and I subtract the square root of x plus 1, that gives me a 0, which a 0 in the numerator is not really a problem, right? However, Since I'm also going to substitute 0 on the denominator in this case, we will get the indeterminate form. Which, if you recall, when we were talking about limits, we were very specific about knowing that the indeterminate form meant that I needed to do some algebraic manipulation to figure this out. But we also discussed that graphically speaking, 0 over 0 means that there's a hole at this location. You with me? And if there's a hole, then there should be a limit. So we are expecting to get an answer here. So now we have to go back into our techniques from limits to figure out how am I going to be able to get rid of this indeterminate form. All right, so I'm looking at this. I'm remembering from my techniques of limits that if I have roots, like a binomial with roots, one of my possibilities that I could attempt would be the conjugate. So that's what I'm going to do. All right, so I'm going to say f prime is equal to the limit as delta x approaches 0 of the square root of x plus delta x plus 1 minus the square root of x plus 1 over delta x. And I'm going to use the conjugate of the numerator. So the conjugate of the numerator would be square root of x plus delta x plus 1. This switches to a plus, and then the square root of x plus 1. Remember, algebraically speaking, I need to balance out anything I do to the numerator, I will also have to do to the denominator. All right, that puts me there. Notice also how I keep writing the limits notation as well as f prime. Personally, my feedback about rewriting f prime, I think personally, as long as you write it in the first line and then you can just put equal, and then on your final answer, you should be fine. However, the limit, you have to write it at each step. Because the moment you stop writing limit, someone that is reading your work may interpret that as, hey, oh, this person already took the limit, so here's the answer to that limit. So that's not the case, right? We have not taken the limit, so you have to continue writing the limits. Okay? All right. So let's do a multiplication. So we have this fraction multiplied by that. This term multiplied by that term will cancel out the roots, leaving me with x plus delta x plus 1. Remember that when you multiply conjugates, the middle terms will cancel out because they have opposite signs. Negative times positive will give me a negative, and then I'll have the square roots of x plus 1 will cancel out the square root. All right. Denominator-wise, I will advise, please listen to this part, that you do not try to distribute the delta x over to the square roots. The reason is, and I want you to think this, when we're going to take this limit, we have to put 0 in for delta x. So if you really think about it, there has to be a way for me to cancel that delta x. If you distribute the delta x, you may not be able to see that. So you actually want to keep it factored out so that if I need to cancel it, which I do need to cancel it, I'm able to simplify the numerator, and I'm hoping, if I did this correctly, that I will be able to factor out a delta x from the numerator so that I can cancel it, okay? So I'm not going to distribute it. Let's see what happens. So square root of x plus delta x plus 1 plus the square root of x plus 1. I'm going to put that in parentheses. All right, as you can see here, if I distribute the negative on the numerator, that becomes a negative x. This will become a minus 1. All right, this x can cancel that x. This 1 can cancel that 1. Which, that's exactly what I wanted to happen, guys. Notice that the only thing that I have left is, in this case, I'm not saying this always happens, but in this specific example, all I have is just delta x by itself, which is amazing. So now I have a delta x on top divided by a delta x, which means I can divide those out, and that leaves me with a 1 on the numerator. So I'll go ahead and take my time to rewrite that. So that means f prime of x is equal to the limit as delta x approaches 0 of 1 over the square root of x plus delta x plus 1 plus the square root of x plus 1. Now you are going to try substitution once again. So by substitution, I can say that if I put in 0 for delta x, this becomes the square root of x plus 1 plus the square root of x plus 1. So we should be able to get then 1 over 2 times the square root of x plus 1, which therefore that means that for this function, the slope is equal to this expression, which it should make sense based on our discussion at the beginning. By observation, this does not have a constant slope, so we should be expecting that we are going to get an expression with variables in it, okay? So now, how is this expression useful? Well, we're not going to get so much to that in this video, but hypothetically, I could be more like, okay, here is this function, find the slope specifically at, I don't know, find the slope at 3. So that's the notation. So remember, this means f prime of 3. That means find the slope when x is equal to 3 for this expression. So now I can go here and say, well, f prime of 3 would equal to 1 over 2 square root of 3 plus 1 is 4. So if I simplify that, that would give me 1/4. Now, I don't have a perfect sketch, but hypothetically, like let's say this is 3, this would be the point that I'm discussing. If I were to draw a tangent line there, the best that I can there, that means that that tangent line would have a slope of 1/4, which is the same slope as the square root function, but only at that position of x equals 3. Cool? Pretty neat, huh? All right. Let's go ahead and try one more problem in this video. Let me go ahead and erase. Now let's say example 2. Let's say for this one that you are given, let's say, what would be good? Let's say f of x is equal to, let's go with x plus 1 squared. Cool. And you are asked to find, let's be a little bit more specific on this one. Let's say you're being asked to find what is f prime of 2. All right, so we don't know any other ways of finding the derivative, which by the way there is. We'll talk about this in the future. But for today, this is all I know, okay? So I'm gonna begin my process by saying f prime. Now what's gonna be different about this is I'm being asked to find the derivative at a specific location. So instead of putting an x here, remember this was also f prime of x, I'm gonna substitute that with a 2 here, cool? So what does that mean? All right, so we will have this. This wouldn't change, but I will have some changes here. Instead of having, since I substituted a 2 for x, then I have to substitute a 2 in for here, and I would have to substitute a 2 in for here. All right, so then what does that mean? I would have to have f of 2 plus delta x minus f of 2 over delta x in order to do this. Okay, so let's go ahead and start simplifying all of that. So limit delta x approaches 0. I need to figure out what f of 2 plus delta x is, which remember, all that means is I need to put 2 plus delta x inside this x. So that would be 2 plus delta x plus 1 squared minus f of 2. So minus, I'm going to put a 2 in for x, so 2 plus 1 squared all over delta x. Perfect. Simplify. All right. F prime of 2 would equal to the limit as delta x approaches to 0. First, I'm going to clean up to facilitate the algebra here. So I know that the 2 plus 1 will give me 3. So it's going to give me 3 plus delta x squared minus 2 plus 1 is 3. 3 squared is 9. So I'm going to go ahead and put a 9 in there. Put the delta x there. Give me a second, guys. Sorry. All right, sorry about that. So now we got the simplified version. I'm going to go ahead and plug in 0 to see what happens for my delta x. So 3 plus 0 will be 3. Square is 9. 9 minus 9 is 0 over 0. Once again, we have the indeterminate form, so we have to figure out how to get rid of that. Remember, it means we have a hole. So I'm looking at this and I'm thinking back to my algebra techniques. Well, what can I do here? I know I need to cancel a delta x. So somehow I need to make a delta x cancel from the top. Now, I know this can factor, but I don't see how factoring is going to help me here. So instead, I'm going to do the opposite. I think I'm going to distribute everything out and see what happens. So I still haven't been able to take the limit. I'm still going to write limit as delta x approaches 0. 3 plus delta x squared. Remember, that's the same thing as saying 3 plus delta x times 3 plus delta x. So I would have to use distribution to get that done. So that will give me 3 times 3 will give me 9 plus 6 delta x plus delta x squares minus 9 over delta x. All right, I don't really need this parentheses. Let me get rid of it. Now I'm going to start simplifying. Notice that on this example, just like on the first example, anything that did not have a delta x canceled out, which, here's my hint to you. If that doesn't happen, check your algebra, okay? Or, quite honestly, there are some functions that are very difficult to try to find the derivative with the definition. Some of those would be like trigonometry, logarithms and whatnot. So luckily, we will explore how can you do this process in a different manner in future videos, okay? So for now, what do I notice here? Well, I can pull out a delta x from here. So if I pull out a delta x, then I would have limits delta x goes to 0, f prime of 2 is equal to, all right, delta x comes out, leaving me with 6 plus delta x over delta x. This delta x's can cancel out. I don't have a lot of room to rewrite this, so essentially I'm just going to take the limit now. The limit as delta x approaches 0 of 6 is just 6. Plugging 0 for delta x gives me 0. So now I just figured out that the slope evaluated at 2 will give me 6. Cool? Now, how is this different from our first example? Well, number one is, by me giving you a number here, I should expect then that my answer should be a constant, because I'm finding the slope at a very specific location. Okay? Now, if I had led this with x's, then I would have to go back and everywhere you see a 2, I would have to replace it with an x, which means that when you got to this step here, it's going to look a little bit different, but everything should still cancel. Everything that doesn't have a delta x should cancel. And when you get to your final answer, you should have an expression that has x's in it. And just like the first example, then you can plug in whatever value you like to figure out the slope. Okay? Now, real quick, let me give you an image again of a visual representation of what was happening. So I have a square function that also got moved to the left one, so it's going to look something like this. Cool. I picked the value of 2, which hypothetically, I know exact location for 2, right? If I plug in 2, 2 plus 1 is 3, 3 squared is 9. So I'm going to say that that point right there is 2, 9. Cool. Now, we just figured out that at that location, the slope is 6. Now, I'm going to kind of try to draw a tangent line again. Not the best, but at least try to show you what that looks like. The tangent line would look something like this. Cool. Now, I'm going to do one more thing in this section, and then we'll finish up our video. I want to know what the actual equation of that line is, okay? So, for example, what I know about that line is, I know that line has a point that is 2, 9, because they share the one point. And I also know that it has a slope of 6. Now, if you recall from Algebra 1, there was this equation called the point slope form. Okay? Now, if I utilize the data that I have, then I should be able to come up with the equation for that line. So that would give me y minus, this is by the way your x1 and your y1, so y minus 9 is equal to my slope, which is 6x minus 2. I'm going to clean that up, and I'm going to multiply it out, so that gives me 6x minus 12, I'm going to add 9, which is 6x minus 3. Which, again, it makes sense. I'm not using a scale, but it looks like I'll have a y-intercept that's -3, so as I can see, it's negative there. It is kind of steep. I can see that the slope is 6 in this case, right? So now, I know that the function that I gave you was this, and I know that the equation that is tangent at this location is y is equal to 6x minus 3. Now, would you agree with me that at that location of 2, 9, this function and this function are exactly the same? Right? We can try, right? If I plug in 2, 6 times 2 is 12, minus 3 is 9. If I plug in 2, 2 plus 1 is 3, 3 squared is 9. So definitely the same, right? But if I go away from it, they're no longer the same, right? Like if I plug in 4, 4 plus 1, that gives me 5, 5 squared is 25. 6 times 4 is 24, minus 3 is 21, so I can see the difference there, right? But stay with me. Would you agree that maybe within this region, they're very similar? So for example, how is this useful? Okay, so I picked an easy example so that we can actually do the math. Like, let's say that I had given you this function and I had asked you, what is f of 2.1? All right, well, you should just be looking at me like, okay, all that means is that I got to plug in 2.1 in here. To facilitate the algebra here, I'm going to turn this into a fraction. So 2.1 is the same thing as saying 21 over 10, right? All right, so what does that mean? That means I'm going to have 21 over 10 plus 1, and then square that, right? I'm like, okay, well, what is that equal to? Well, we know that 1 is the same thing as 10 over 10, so I can add those up. So that gives me 31 over 10 squared. So I would say f of 2.1 is equal to, all right, now, I don't know about you, I would say the average person can't really do this mentally, right? So they may struggle a little bit getting this, but let's try. So we know 10 squared, we know that one's 100, right? All right, so what is 31 squared? Oof, okay. Well, 31 squared. If we're not sure how to do that, a good little trick you can use is you can utilize like 31 times 10, right? That's gonna give you 310. If you're gonna do this 3 times because it's times 30, right? So we have 31 times 10 we said was 310. It's happening 3 times. And then I can add 31 to that. Cool? All right, so what does that give? Well, that's gonna give me 930. Cool. 930 plus 31 will give me 961 over 100. So you're looking at me like, okay, cool, man, what does that have to do with what we're doing? Okay. This tangent line can be useful, basically. Sometimes you'll be asked to like, hey, can you find an estimate, not the exact thing. Can you use this tangent line to find an estimate? So instead of saying, what is f of 2.1 by plugging in, I can go and say, sorry, it's getting all messy. F of 2.1 is approximately, instead I'm going to use this tangent line. So that will be 6 times 2.1 minus 3. Okay, so now the algebra is a lot easier here to do, okay? So I'm going to use the approximation. So 6 times 1 is 6. 6 times 2 is 12, so it's 12.6 minus 3. So approximately, if I take away 3, we're looking at 9.6. Cool, so I am claiming that f of 2.1 is approximately 9.6. Now, we know based on this that the exact answer of f of 2.1 is equal to, if you really look at that, 9.61. Isn't that pretty neat? Like, look at how difficult, and it wasn't that crazy if I'm being honest with you, to figure it out, the exact value was versus how easy it was just to use the tangent line. Now here's the key. The tangent line can only give you close approximations if you pick a value, so in this case 2.1, that is close to the value that they share. So in other words, we can use tangent lines to come up with very close estimates for any function as long as I'm close to the tangent point. Now, again, this seems kind of silly for the example I picked, But I want you to imagine if I had a much more difficult function, cool? Like a function of, if I go back to my first example where I had the square root of x plus 1, right? And you were asked to figure out, like, I don't know, what is the square root of 3 without a calculator to get an approximation. Some of you guys are very good with number sense, so you'll be able to give me an approximation. Some of you guys may not be able to do that. So instead, what you could do is find a tangent line that is close to the location that we're trying to find the square root of, plug into that tangent line, and you're going to be able to get a very good estimate of what that actual value is. Cool? All right. Anyway, so that's at least 2 examples to help you out dealing with how to find the derivative using the definition of the derivative. Keep in mind, my last advice is obviously the functions can get a little bit more difficult. Go back and think about your processes for limits. Don't forget that you can use conjugates. Don't forget that you can use factorization. Don't forget that sometimes you just have to clean up. What I mean by that is do distributions, combine like terms, get common denominators, combine like terms. Use your algebra skills to combine terms. And remember, when you get to the step where you do all your mathematics, for example, on this one was, the way you're gonna know if you did it correctly is the numerator should only have terms that have delta x on it so that you can factor it out and cancel it out. Cool? All right, thank you for watching.